Work done by gravity. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. We will now concentrate on the work done by a very special force, namely the weight of a body. Remember that weight is mass times acceleration of free fall and is directed vertically down. Thus, if a body is displaced horizontal, the work done by weight is zero. In this case, the angle between the force and the direction of motion is 90 degrees. We next examine the work done on an object by the gravitational force acting on it. If an object falls a certain distance, work will be done on it by the gravitational force that is acting on it. We consider two different situations for the analysis of work done by gravity. First, the body is subjected to a single force due to gravity in vertical motion. Second, the body is subjected to a single force due to gravity in motion along incline. For the sake of simplicity, we will start by making the assumption that air resistance is negligible and the body slides on incline without friction. If the body falls a vertical distance h, the force of gravity is parallel to the displacement. The angle between the direction of force vertically down and displacement vertically down is 0 degrees, as shown in the diagram. Then the work done by the weight is mass times gravity times height. Suppose now that instead of just letting the body fall, it slides down the ramp traveling a distance L. We calculate the work done by the weight. Theta is the angle between weight and incline. We are not given theta in the sketch, but from the right triangle that forms the incline, we see that the cosine of theta is the height divided by the length along the incline. We replace cosine of theta with h divided by L. Once cosine of theta is determined from the geometry of our sketch, it is straightforward to calculate the work done by gravity. The work done by the weight is mass times gravity times height again. This result is exactly the same as for the vertical motion, and it shows that the distance L cancels. Hence, the work depends on the height h, but not on the distance. This means that the work done by gravity is independent of the path followed and depends only on the vertical distance separating the initial and final positions. A body of 60 kilograms falls from the terrace of a building 80 meters high. Calculate the work done by gravitational force. Look at the diagram. The body falls under the action of the force of gravity. To calculate the work done, we will use the equation above. Replace m with 65, g with 9.8, and h with 80, and perform the calculations. A worker lifts a 10 kilograms box vertically upwards 95 centimeters from the floor at constant velocity. He then sets the box back down on the floor. How much work does he do when lifting the box and when setting it back on the floor? Look at the diagram. A force equal in magnitude to the force of gravity is needed to lift or lower the box at constant velocity, since the net force must be zero. Therefore, the magnitude of F is mass times gravity. When the body lifts, the force F acts in the same direction as the displacement, so the worker does positive work. The worker does 93.1 joules of work when lifting the box. When the worker sets the box back down on the floor, the force F acts in the opposite direction as the displacement, so the worker does negative work. The worker does minus 93.1 joules of work when setting the box back down on the floor. Anytime we lift an object, we do work against gravity. When the body is lifting in the upward direction, the weight is acting in the downward direction, but the displacement of the body is in the upward direction. Since the angle between the weight and displacement is 180 degrees, the work done by the weight on the body is negative. When the body is falling down, the weight is acting in the downward direction. The displacement is also in the downward direction. Thus, the work done by the weight on the body is positive. Work done by a varying force. So far, we've defined work done by a force which is constant in both magnitude and direction. If a constant force acts on an object and makes it move a distance in the direction of the force, the work done on the object is force times displacement. The diagram shows a graph of force against distance in this situation. The area under the line is a rectangle of height representing the force and of base length representing the distance moved. In fact, the work done by the force is found by calculating the area under the graph. So far, we've considered work done by constant forces only. The work done by a constant force of magnitude F that displaces an object by distance d is given as force times distance. However, work can be done by forces that vary in magnitude and direction during the displacement of the body on which it acts. When a force varies as it pushes or pulls an object, one cannot simply calculate work as the product of the force and distance. After all, if the force doing the work is not constant, what value are we going to use in the calculation? Yet many common situations involve non-constant forces, such as the force exerted to stretch a spring. Springs are very important because they serve as simple models for lots of complicated physical systems. We next want to examine the work done by spring force, the force from a spring. Consider a horizontal spring whose left end is attached to a vertical wall. If we apply a force F to the other end, we will stretch the spring by some amount x. When we stretch a spring, it gets more and more difficult the longer it gets. The force needed to stretch the spring is directly proportional to the extension of the spring. The force exerted back by the spring is known as Hooke's law. F sub s is the force exerted by the spring. X is the displacement relative to the unstretched length of the spring, and K is the spring constant. Pulling to the right a spring stretches the spring to the right, which results in the spring exerting a force to the left. The spring force is called a restoring force because the force exerted by the spring is always in the opposite direction to the displacement. This is why there is a negative sign in the Hooke's law equation. Since the force F and the extension x are directly proportional, the graph of force versus extension is a straight line through the origin. It will look like the graph as follows. The work done as the spring is stretched is found by calculating the area under the graph. The shaded area under the line is a triangle in which the height representing the force and the base length representing the distance moved. We replace F with K times X to get the formula to find the work done in stretching a spring. Calculate the work done by the force represented by the figure. Work is not always force times distance, but it turns out that the work done by any force will always equal the area under the force versus position graph. So we must find the area of the trapezium in which the height representing the force and of base length representing the distance moved. We now perform the calculations. A spring is stretched to a position 35 centimeters from its equilibrium position. At that point, the force exerted on the spring is 10.5 newtons. Calculate the work done in stretching the spring. We have the extension x and the force. But to find the work, we need to calculate the value for K, the elastic constant for the spring, using Hooke's law. We now take the formula above to find the work done in stretching the spring. A 5 kilograms mass is attached to a spring and allowed to fall. The mass rests after the spring extends by 50 centimeters. Calculate the work done in stretching the spring. The mass is at equilibrium after the spring extends, so the weight equals to spring force. We now find the elastic constant for the spring. We now take the formula above to find the work done in stretching the spring. Perform the calculations.